Assalamualaikum. Welcome to the lecture number 30, and we will discuss a problem related to section 6.1, that is shear stress due to transverse load. Okay, and we will be solving problem number 6.4, 6.19, 19, 6.22, and 6.24, and from these topics. Okay, let's see. First problem. A square box is made up of two 20 by 80 millimeter plank and 220 by 120 millimeter plank. Now, if you look at this wooden box, wooden beam, square box beam is made up of 20 by 120 millimeter plank, top and bottom, and on the side it's a 20 by 80 millimeter plank. So it's a box beam. Dimensions are given. Okay, knowing that the spacing between the nails is 30 millimeter. Between these are the nails, the distance S is given, that is 30 millimeter. And the vertical shear in the beam is 1200 Newton. So the shear is acting, if you take any section, the shear force is acting, internal shear will be equal to shear force, that is 1200 Newton. Part A, we have to find the shearing force in each nail, and second part, the maximum shearing stress in the beam. Okay, now let's start with the part 1, but before that we have to find some properties, cross-sectional properties. Okay, now if I look at this beam cross-section, if I draw the cross-section, so we have, it's a box beam, and it is made up of 4 planks. Okay, and we have a nails. Okay, now in order to calculate what will the shear force on nails, we have to calculate what is the shear flow first on these region. So in order to calculate shear flow for this region, we have to calculate the value of we have to calculate first moment of area for this shaded region. Okay, now we know that the shear flow, we already know shear flow is Q is equal to VQ over I. So I for the whole cross section, Q for the shaded region, and we know, so we get the value of shear flow. Now shear flow, if we multiply with the nails, spacing between nails, it will give us the force on each nail. Okay, now if you look at this shaded region, the Q will be calculated for the both of the nails. So we have, since we have to calculate shear force on single nail, each nail, so what we will do, so the force on nail will become Q divided by 2, that is for single nail, and multiply by distance S. Okay, let's start. So first we have to find I, we have to calculate, so let's calculate I. So it's very simple, outer square minus inner square, we will get the value of I. So this will be for outer one, this will be 1 by 12 BH cube, B will be 120, H will be 80 plus 20 plus 80 plus 20, again 120, VH cube minus the inner one 1 by 12. So B will be, so this is 20, this is 20, so this will become 80, 80 by 80. So 80 by 80 cube. So if you put the value, so we have the value of I will be 1 by 12, 120 by 120. So let us calculate. Okay, the I will be 1.3867 10 to the power minus 5 meter 4. So we will convert into meter. Now, for the part A, we have to calculate the value of Q for the shaded region. So let me calculate the Q for this region. So that Q will be simply, let me write Q1. So that will become area 1 and Y1. So Y1 will be simply distance from the centroid of this section to the centroid of this area. So that will be my Y1. Okay. Now area. So let me calculate Q1. Area will be simply 20 multiplied by 120. So in terms of meters, 0.12 multiplied by 20, and this distance. So we have 40 plus 10, that will become 50. So if from center to over here, that will be 40 plus half of this width, that is 10. So this total distance will become, Y1 will become 50. So we will write over here, sorry, this we will take in meters. So let's take in meters. So 0.02 multiplied by distance 0.05. So if we calculate this, so 0.12 multiplied by 0.02 multiplied by 0.05. So this will become Q1 will be 1.2 10 to power minus 4. Now, for the maximum shearing stress, so for the maximum shearing stress, we have to calculate till centroid of the section. Means for the maximum shearing stress, we have to calculate Q from above region plus this region. So this region, let me write 1 over here, plus 2 plus 3, because the maximum shearing stress will be at neutral axis, and that neutral axis will be passing centroid of the section. And we know that the formula for maximum for the shear stress is tau V Q over I T. Now this time we have to calculate Q till midsection, and T will become this dimension plus this thickness plus this thickness. Okay, so let me write Q2. Let's calculate Q1 and Q2, and then we will solve accordingly. So Q2 will be equal to Q1 that we already calculated plus 2 times Q2 because due to symmetry, so Q2 is equal to Q3. So Q2 will be simply 1.2 10 to power minus 4 now plus 2 times Q2. Q2 will be area, the area of the shaded region. That will be what? That will be this dimension, the width, this dimension or this dimension will be 20 and the height will be 40, half of 80. So we can write the area will be 20 multiplied by 40 of 40 multiplied by 20, 0.04 multiplied by 20, 0.02. And the distance from the center of this section to the center of this one, so this total height is 40 and half will be for half will be 20. So the distance will be become multiplied by 20 millimeters, 0.02. Now if I calculate Q2, so the value of Q2 will become so let's calculate to multiply by 0.04 0.02 multiply by 0.02. So this will become so this will become 1.2 10 to power minus 4 plus 8 into 10 to power minus 5, and Q2 that we will use to calculate the value for the maximum shear stress. So this will be equal to 2 times 2 into 10 to power minus 4 meter cube. So we have the values of Q1 and Q2, and now we calculate the force and the shear stress. Okay, now let's calculate what will be the value of force on each nail. We know that for the force we have to calculate shear flow. For that upper region means the shear flow for this region. So Q V Q over I. We know the value of force, that is 1200 Newton. Q for this one, so let me write Q1 over here. Q1 we already calculated, that was 1.2 10 to power minus 4 divided by I. We also calculated, that was equal to 1.3867 10 to power minus 5. So if you calculate, so this will become 1200 multiplied by 1.2 divided by 1.3867. So the shear flow will be equal to, Q will be equal to 10384 into 0.36 Newton per meter. So this is a shear flow for both nails, for the upper both nails. For single shear flow, the force, now force will become on each nail, that will be Q divided by 2, that is shear flow on single nail, multiplied by S, the distance. That is given, that is 30 millimeter. So let's put the value 1.10384.36 divided by 2, and the nail spacing is 30 millimeters, so we put 0.03 meter. Now if we calculate, so this will give us the force on each nail. 3603. So force on each nail, if we calculate, so force on each nail will be equal to 155.76 Newton. So that is the force acting on each nail. So that is part A. Now, for part B, we have to calculate shear stress on the beam. So for the shear stress, we know that shear stress, maximum shear stress will be equal to VQ over IT. Now, obviously, we have to calculate uh, for the section passing through the centroid. So this whole region, we already calculated Q for this whole region. So we know the force, shear force, that is 1200. We calculated Q for the whole region, that is 2 into 10 to power minus 4. I we calculated was 1.3867, 10 to power minus 5. Now T. So T will be this thickness plus this thickness. So this is this thickness and this thickness. So this is 20 plus 20, that will become 40. So this value will become 0.04. Okay. Now, if I put the value 1200 multiplied by 2 times 4, so this will be 1.3867 divided by 0.04. So tau max will be equal to 4.3 to 10 to power minus 10 to power 5 Newton per meter square, or we can write 0.432 mega Pascal. So that is tau max acting on this section of the beam. So this is how you calculate maximum shear stress, and previously we calculate part A, we calculate the shear force on each. Okay, let's see problem 6.19, and in this problem the statement is given: a timber beam AB of length L. So this beam AB of length L is shown over here, and a rectangular cross section carries a single concentrated load P. So rectangular cross section and the single concentrated load P that is acting at the midpoint C. Show that the ratio of tau max by sigma maximum of the maximum value of shearing to normal stress in the beam is equal to H by 2L. So the ratio between tau max by sigma max is h by 2l, where h and l are respectively the depth and the length of the beam. H is the depth of the beam for the cross section is given, and L is the length of the beam. That is part A. And part B, determine the H and the width P of the beam, knowing that the length 2 meter, P is 40 kilonewton. Tau max, the maximum shear stress is given, that is 60 kilopascal, and for the sigma m, that is 12 megapascal. So we have to find these values uh, based on the shearing stress and the maximum shear stress and maximum normal stress. Okay, now let's find the value. So what we will do, we have to find what will be the maximum shear force acting on this beam and what will be the maximum bending moment. For that we have to draw shear force and bending moment diagram. For that, first we need a reaction. So it's a simply supported beam with the load at the midpoint. So at A, the force will be P by 2, and at P, the force will be P by 2. So you can easily calculate what will the force is. Okay. Now for the shear force diagram, so let's take a section. So let me change the color. So let me say take a section between A and C, just over here, and let me draw a free body diagram for that section. For that section, so we have shear force acting downward, where we take positive, and we take bending moment acting like this as a positive, counterclockwise, and we have a force of P by 2. And V, if I write P minus P by 2, and this will be equal to 0, so V is equal to P by 2. So now taking this length as x for bending moment, so M minus P by 2 into x is equal to 0. So M is equal to P by 2 times x. Now x is equal to 0, so MA will be 0, where x is equal to 0. And we have at C, where x is equal to L by 2, that is at C, so MC will be simply P L by 4. So if you put x is equal to L by 2. Now, and the bending moment, now if I take a section just like over here, and let me change the color, and if I draw free body diagram, okay, let me take section from left to right, and you guys can practice from right to left. So this we have P by 2, one force P acting downward over here, so shear force V positive and bending moment M. So V plus P minus P by 2 is equal to 0, and V will be simply minus P by 2. And for the moment, let me write over here. So moment will be M. Okay, now this distance is x, and this distance is simply L by 2, and you can say that this distance will be x minus L by 2. So moment will be equal to plus P times x minus L by 2 minus P by 2 into x is equal to 0. So moment equation will be equal to by 2 times x plus, sorry, not plus, that will become minus. So let me remove over here. So this will become minus p x minus L by 2. Now, if I put x is equal to L by 2, so this term will cancel and we will have MC again. So if I put x is equal to L by 2, so this will lead me to, this will lead me to this expression of PL by 4. Now if I put x is equal to L, that is at B, so MB is 0. Now the variation is linear. Now if I draw Shear force diagram, so the Shear force diagram will be simple. Let me, so Shear force, so from A to C, let me put C over here and there B. From A to C, it will be positive P by 2, and it will change at C, and it will be negative P by 2 at P. And the bending moment, again let me put C and B, so it will start from 0 at A, and it will be maximum at C, and the maximum value will be PL by 4, and again it will be 0 at B, and this is a symmetric triangle at C. Okay, so the maximum Vmax we can write is P by 2, and the Mmax is PL by 4, and we will use these value to find the ratio of tau max by sigma max, and we will find the value, rest of the values. Okay, now let's solve section A, part A. For this problem, we know the Vmax and Mmax, and let's see. Now since it's a rectangular cross section, so tau max for rectangular cross section is 3 by 2 V by area. Right? So, and we know that the maximum force V was simply P by 2, and the area is B multiplied by H. So tau max we can write 3P divided by 4 times BH. Now sigma max is MC over I, so M max, or we can write M divided by S, that is section modulus. Now bending moment, maximum bending moment we already calculated, that was equal to PL by 4, and section modulus for the rectangular beam is equal to 1 by 6 BH square. So this is 1 divided by S. So S for the rectangular section is 1 by 6 BH square. Now if you put the value, so this will become, if I simplify it, so this will become 3 times PL divided by 2 times BH square. Now tau max by sigma max, tau max by sigma max. So if you put the value, So that become 3p divided by 4ph divided by 3pl divided by 2bh square. Now 3 will cancel out, right? So this 2 will 2 this will become 2, this will cancel out, p will cancel out, b will cancel out, and we'll have h will cancel h square, and what we will left, if we simplify it, it will be simply h by 2l. Now which is equal to this value that we calculated over here, that is known over here. So tau max by sigma max for this type of beam unloading is equal to h by 2l. Okay, so this is part A. Now part B, we have to find, we know the length, we know the p, we have to find tau max, and sigma max is given, so we have to find the value of h and b. So what we will do, we will take the ratio of tau max by sigma max, and we will calculate h, and we will use that h to put the value in tau max, and we will calculate the value of p. Okay, so for part B, so we know that tau max by sigma max is equal to h by 2l, and sigma max is given, that is 90 kilopascal, 960 kilopascal. Sigma max is given, that is 12 megapascal. Now h we have to find, and we know the length of the beam is given, that is 2 meter. So if you put the value, so h will be equal to, when we solve it, that is equal to 0.32 meter, or in terms of millimeter, that is 320 millimeter. Now from now we can calculate the value of b from this equation. Tau max is equal to 3 by 2 times v divided by area, right? And we know that this was equal to 3 p max. P max was p by 4, p by 2, and the area is b into h. We already calculated the value of h, so this will be 960 kilo Pascal, 3 by 4. P we already know, that is given, that is 40 kilonewton. B we calculated, H we calculated from the previous relationship, and multiply by B. So when we simplify it, so B will become 0.0977 on meter, or we can write 97.77 millimeter. So by using the values and the relationship, we calculate what will be the required dimension for that timber beam. Okay, so now let's see another problem related to this topic. So okay, now calculate the value of shear stress at point A. So part A for problem 6.22, we have to calculate shear stress at A. So we write V QA divided by I times T. For that, let us take this half section. So we have to calculate Q for this shaded region. And since at point A, so this thickness will be 20 millimeter, and we have to calculate first moment of area for this shaded region. So QA will become 80 multiplied by 20. Okay, now the distance from the center, sorry, first let me write the expression. So the expression will be simply area of that region and distance from the centroid of the whole section. So area 80 multiplied by 20, and y naught. Y naught will be the distance from the centroid of the section and this center. So this total distance was 35 millimeter minus 10, so that will become 25 millimeter. So let me put over here 25. So QA will be simply 40 into 10 to power minus, 10 to power 3 millimeter 4. Sorry, cube, not 4. Or QA in terms of meter, it will be 40 into 10 to power minus 6 meter 4. Now let's calculate shear stress, and TA will be thickness at that point A, and it will be 20 millimeter or 0.02 meter. So let's put in the above equation. So tau A will be 90 kilonewton. We already calculated this value, and we already QA is 40 10 to power minus 6 divided by I was 5.8133 10 to power minus 6, and we calculated, we know the value of TA, that is 20 millimeter 0.02. So tau A is 31 10 to power 6 Newton per meter square, or 31 megapascal. Okay. Now part B. So for part B, let me change the color of the pointer. So let's calculate part B. So that will be simply tau B V QB divided by I and TB. Now for B part, so let us take this, instead of above region, we will find Q for the bottom region, and it will give us the same value. So we don't have to calculate from above, so we can calculate first moment of area from the bottom. So that QB, I can write AB and YB. So QB area for this will be 30 multiplied by 30, and the distance from this center. So this distance, we know that total distance was 65 millimeter, that will be calculated from previous. So that will become 65 minus 15, so that will become 50 millimeter. So this distance YB will be simply 65 minus 15, that will be 50 millimeter. So that becomes 50 millimeter. So QB, if you calculate, so that become 30 10 to power 3 millimeter cube, or 30 into 10 to power minus 6 meter cube. Okay, now tau b and TB, the thickness over there is 20 millimeter or 0.02 meter. So tau b, we all know the value of shear force, 90 kilonewton, and the area, we already calculated Q, 30 into 10 to power minus 6. Value of I is 5.8133 10 to power minus 6, and TB we calculate 0.02. So tau B, if we solve it, that is 23.2 10 to power 6 Newton per meter square, or tau B we can write 23.2 megapascal. Okay, so the location we are interested, we have to calculate first moment of area about that location, and T will be accordingly. Okay, now in the second question, let's see problem 6.24, that we have to calculate the maximum shear stress. So tau max will be V Q over I T. Okay, now for that we have to calculate the value of Q. Now the maximum shear stress will be acting on the neutral axis or acts on the centroid of the section, right? So we have to calculate over this section or over this location, and for that we have to find what is the first moment of area for this shaded region till neutral axis. Now in order to calculate this, so means that let me draw over here again. So we have to calculate Q for this section. I'm taking this, drawing this shaded section. So this is 1, 2, and 3. So Q, that is equal to A naught Y naught. So this will become for this problem Q1 plus Q2 plus Q3. Q2 and Q3 are same, so Q1 is equal plus 2 times Q2. I can write like this. Okay, now Q1 will be A1 Y1 and 2 times A2 Y2. So area 1 for first one, so that is very simple, that is 160 multiplied by 20. Now what will be the Y1? This dimension is 35 millimeter, and we calculated this one was 65 millimeter. Now from this centroid, this location, what will be the value? It will be simply 35 minus 10, so it will become 25 millimeter. Plus 2 times area. Now this total is 35, so this will become 15. 35 minus 20, that will become 15. So 15 multiplied by 20, and now the center will be lie at the 15 divided by 2, so that is become 7.5. So if I calculate the value of Q by multiplying these value, so the value of Q will be 84.5 10 to power 3 millimeter cube, or in terms of meter, Q is 84.5 10 to power minus 6 meter cube. I for second moment of an area um, we already calculated, so that was 5.8133 10 to power minus 6 meter 4. Now thickness. Now thickness, since we are calculating on this location, on this point, so thickness will be this plus this. So that is, this one is 20 and 20. So T we can write 20 plus 20, that is 40 millimeter, or in terms of meter 0.04 meter. Okay, now let's calculate tau max. We have all the required information. So tau max will be V. We already calculated 90 kilonewton. Q for this region we calculated, and that was 84.5 10 to power minus 6 divided by I. We calculated previously 5.1833 10 to power minus 6, and T is 40 millimeters, 0.04. So tau max is equal to, if we calculate, that will become 32.7 10 to power 6 Newton per meter square, or tau max is simply 32.7 megapascal. Now, this was problem 6.24. We have to calculate maximum shear stress. Okay, now if you look at, you can also calculate maximum shear stress by using this area. So if you can calculate Q for this area on this black area, you can use that area as well to find the value of Q. And if you calculate from that, so let me write this Q bar for that shaded region. So tau max will be V Q bar divided by IT. So it will give you the same value as the calculated over here, that is 32.7 megapascal. So whichever area integration for first moment of area you will take, it will give you the same value for that location. And this is how you will calculate shear stress under transverse load. Okay, now in this lecture we solved problem related to section 6.1 using the shear flow in case of beam nails. When we calculated forces on the nails, so the shear flow is simply VQ over I, the formula, and we calculate the shear stress for the different problem, and we also calculate the maximum shear stress, and the value was tau is equal to VQ over IT. Now if we have a rectangular cross section, so the tau max will be equal to 3 by 2 times V divided by area. So that's, you can calculate the stresses and the shear flow acting on any cross section or member under transverse load. Okay, thank you very much.